Okay, let's look at another example. Before I explain this example, if you look at it carefully here, I talked about using a gas. Now I'm using hydrogen, and I want you to know that hydrogen is you just treat hydrogen like any other electrode, but if you look at it, you can see it's in gaseous form. And anytime, one important thing we need to know is that anytime we are using a gas, we usually use an inert electrode. Can see here, this is the inert electrode, and the example of inert electrode we normally use is platinum and carbon, platinum or carbon. So here we are using platinum, take note of that. And because hydrogen is a gas, you can't connect a wire to a gas, so you have to introduce an electrode, and that electrode that will not take part in the reaction, so we call them inert electrode, meaning that it is unreactive. The platinum is not really taking part in the electrode. It's only serving as a medium through which the electron is going to flow. So if you look at everything we have here, that this is what we call standard hydrogen electrode. We call it standard hydrogen electrode, SHE. You can see that the hydrogen gas is coming in from here, and goes out from here. So there is a constant supply of hydrogen gas. So at any point in time, remember that this is a glass. It's a glass, is transparent. So you can see the platinum inside. You can see here. Platinum you will not forget, because we live in a platinum province, which is the northwest. You can't forget. You can see the platinum here. And on this side, we are familiar with copper. You can see the copper here. So the copper is there, but we are using the electrode here is active. This is an active electrode because it's taking part in the reaction, but this one is an inert electrode. It's not taking part in the reaction. So if you also go through the standard reduction potential table, you can also see that the same things apply. That here, anytime you can see anywhere the oxidation is taking place, electron will be coming out from there, because that is where you lose this electron. So in other words, oxidation, you can see anywhere oxidation is taking place, you can see the electron is coming out from there, because that's where we lose electrons. And remember, oxidation always takes place at the anode. On the other compartment, you have reduction, which we have discussed in detail before, and the cathode. And the reduction will be taking place at the cathode. So you can see in an examination, you may be asked to state the conditions here that is taking place here. That's where you include 1 atmosphere being the condition of pressure. 1 atmosphere. So the pressure of this gas must be 1 atmosphere. The concentration of the solution must be 1 mole per dm cube, and the temperature must be 25 degrees Celsius. And we still have the salt bridge there. Remember that in our salt bridge, we should have a cutting wall here, a cutting wall, and we also have a cutting wall here. Remember the essence of having a cutting wall here. We want to use something that is porous, in such a way that the mixture we have here at the salt bridge and the mixture here, they are not going to mix up together, but that material must be porous. The ions must be able to move freely from either of them.